Beneath this pleasant landscape lies oil. Deep down below our feet, its presence made known only by the unexpected. Nodding pumps, tank farms and measuring stations, derricks where drilling still goes on. Scant sign of the great oil fields beneath jungle, desert, lake and ocean. The oil man's first questions are, how big are they? How deep? Imagine a city embedded in the earth, anywhere from 3,000 to 20,000 feet down. A single oil accumulation could be as large. And up through these boreholes, only a few inches across, but sometimes 4 miles long, must pass all the information the engineer needs, thousands of feet up through the Earth's strata. Guided almost by a sense of touch, the driller probes down miles beneath his feet, knows what rocks he is piercing at the end of his drill pipe, and what his bit will raise to the surface. As the drill gouges deeper into the earth, these samples from a mile or more down will guide the geologist in his search for the rock layers likely to contain oil. And in the laboratory, the paleontologist will follow the clues of fossil fern and shell. This electrical probe, or sonde, alternates with the drill to make soundings of the borehole. Changes in the rock structure cause changes in the flow of current. Recording these on a continuous chart still further narrows the search for oil-bearing layers. So the evidence builds up from the carefully patterned network of wells and is pieced together into a model of the reservoir below. A model in 3 dimensions of what the oil man can never see. But when the oil is proved, there must still be pressure to drive it to the surface. From the surface down, the Earth's formations are usually soaked with water, distributed in a mesh of tiny pores. This acts as a column, generating tremendous pressures deep in the Earth, like the pent-up force of a spring. Lighter than the blue water, the white gas and yellow oil separated upwards as they formed millions of years ago until they were trapped by impermeable rock. And here the gas, under a rock dome, has formed a cap. So the oil remained, imprisoned under pressure, until the drill bit down, to release the force which the oil man must stem when he caps his well. Now, the difference in pressure between surface and reservoir causes tiny bubbles of gas to appear in the oil and expand. They rush up the borehole, driving the oil with them. In this analogy, carbon dioxide drives some of the liquid out, but much is left behind. Where there is sufficient underlying water, oil will be forced up from below. This is called natural water drive. The higher in the layer that the engineer drills, the longer will the well go on producing oil. When the layer contains gas under pressure, the oil will be driven down toward the borehole. This is natural gas drive. If, as here, the borehole is not deep enough, soon only gas will be produced. With the field coming into production, the engineers work out its content and its best rate of yield for a life of 10 years, or 20, or even 50. In these calculations, the viscosity of the oil is important and should be measured under the actual temperatures and pressures of the reservoir, as can be done in this apparatus. A pressurized cylinder containing a steel ball is rocked to mix together the original proportions of oil and gas. The cylinder is then lowered into a hot tank to warm it up. A stopwatch records the time taken by the ball to slide down inside the cylinder against the resistance of the oil. This gives the viscosity directly. Rock samples again, but now of the oil-bearing layer itself, and under test is the permeability of the rock. Pressure is needed to drive a liquid through it, and the finer the pores, the higher is the resistance to pressure. A standard core sample is sealed into this rubber grommet. In this apparatus, air pressure is applied to one surface. A sensitive manometer indicates the pressure drop across the sample, and so measures the permeability. Finally, pore space, the space occupied by the billions of pores whose volume measures the rock's capacity for storing oil. Weigh the sample saturated in a liquid. Subtract the dry weight, and you can calculate the pore space of the rock. In the field, constant check is kept on conditions within the reservoir. This instrument is pulled to the surface after lying at different depths in the borehole where it has been recording changes in temperature or pressure. Clockwork timing mechanism turns a chart of copper foil on which a stylus scribes a continuous record. These complex conditions are further studied on models in giant pressure chambers, as well as by slivers of rock beneath the microscope. Many months of intricate calculation are needed to arrive at an accurate forecast of the behavior and productive life of the oil reservoir, which no man will ever see. In this task, the electronic computer plays an increasing part. It's a tremendous help to swift calculation, but no substitute for the human mind. Now the field is producing. By pipeline, by tanker, by rail, the crude oil moves out across the world. And in his laboratory, the engineer checks his estimate of the oil that remains in the field. As in the viscosity test, he puts a sample of oil and gas under the temperature and pressure that existed in the reservoir when it was first tapped. Next, he allows enough of the oil sample to escape to reduce the pressure